Okay, so now we're looking at power series. And as we said before, a power series is any infinite series that has the following form. Where we think of x as being a variable, a as being a fixed number that we call the center of the power series, and the coefficients Cn are also going to be real constants. So this is just again a fixed real sequence. And we said that power series are infinite series, so there's nothing new there. And the tests we're going to use for determining if a power series converges are going to be the same tests we use for an infinite series. But the one thing that's going to be different is we notice that the value to which the power series converges is going to be dependent on x. In other words, the power series itself is a function of x. And that makes it different than just a regular infinite series. Because now we have to worry about what values of x the power series is going to converge to. And so this is basically the radius of convergence. So we mentioned before that the radius of convergence of a power series can be defined as the set of all real numbers x such that the power series converges. And I'm going to write this p of x, okay? P of x converges. Okay, and we made this observation that if we have a given value that's a certain distance from A and the power series converges for that value, all the other values closer to A are also going to converge too. Okay, so this is kind of an important point. So generally this is going to be a symmetric interval. This is generally an open interval about A. So we could think of this as, A minus R to A plus R. Okay, the endpoints may or may not be included. In other words, this power series may or may not converge at the endpoints. We're going to have to test those differently. Okay, so let's look at the radius of convergence a little bit more. So we've talked about the fact that whether or not the power series converges can depend upon the value of x. And I'm going to give you two examples. One's going to be an example where the convergence of the power series does depend on the value of x, and the other will be an example where it doesn't. So let's look at the geometric series, okay? We're all familiar with that. Now you notice that if I simply replace r by x now, okay, it's still a geometric series, okay? And we know that the geometric series converges when the base has a magnitude less than 1. So this is clearly showing us that this is a power series that only converges when the absolute value of x is less than 1. So here, the radius of convergence is 1. And the center is 0. Okay? So if I put x equal to 2 in, this power series won't converge. If I put x equal to a half in, it will. Now, we're going to show in the next section that the power series for e to the x is given by the following infinite series. And if we go ahead and use the ratio test, we'll see that this actually converges for all values of x. So remember what the ratio test says. The ratio test says that we take the limit as n goes to infinity of a to the n plus 1 over a to the n And if that's less than 1, the series converges. And when you do this test, what you'll see is, you'll see that you're taking the limit as n goes to infinity, and this will end up being x over n plus 1, which clearly goes to 0 for any x. So this shows us this power series converges for all values of x. And so here the power series is not dependent upon what the value of x is. Okay. Now, generally, we're going to be considering power series where the center is 0. Okay. And I'm going to kind of assume that unless we specifically say otherwise. There will be a few cases. And what I want to point out is what I mentioned earlier is that if the power series converges for some value x naught, it's going to converge for all values in that interval. And the reason why is, if you look at this, if you look at the power series, let's go ahead and let this be A. Okay. And this is going to converge. And let's assume that all the CNs are positive here, okay? I'm going to make that x sub naught. And now you notice that if x is less than x naught, then this implies that x to the n is less than, and we'll say less than, is less than this. And if the CNs are all positive, it tells us that this is true. Well, let's say they're all non-negative. So we could actually have, okay, for all n, which tells us that by the comparison test, this series also has to converge. Okay. Now, there's one very important thing that we should mention, which is the following. This is an important result that we haven't had to use up to this point, but we're going to use now. And this is the fact that if a series converges absolutely, it converges conditionally. So this is an important theorem. Then it converges conditionally. What do I mean by that? Here's where I'm headed with this. Suppose all the CNs are greater than 0. Okay, and I know that this power series converges for a positive value of x. Okay, this converges. This implies that this same power series has to converge when x is less than 0. Notice that when x is less than 0, this becomes an alternating series. Okay? And although you can't prove it with the alternating series test, it's not too difficult to show that this statement is true. And so notice why we want to bring this up is because if I know that this series converges for x naught greater than 0, I also know it converges for negative x naught. Okay? And so that's the key thing, because now if we know this is true, and we know that it converges for x naught, it converges for x, which means it also converges for negative x. And this is what gives us this notion of a radius of convergence. Okay, this notion that if we just let this be 0, and when we have any value over here that's positive, and the series converges here, it also has to converge for the negative of that value. Okay, that's a very important point. We're going to use that a lot. Now, why is the radius of convergence important? Okay, well, the radius of convergence is important because there are a lot of functions that can only be defined by power series. So, for example, the exponential functions, the trig functions, the log functions, they can only be defined in terms of a power series. And naturally, we want to differentiate and integrate these functions. And so the question is, how do we integrate a power series? Well, we'd like to say it's term by term, but we can't just say that. When you start to distribute integrals across infinite summations, things can go very wrong. Okay, and I won't show you examples, but that's just a mathematical fact. We can't always do that. We can distribute an integral across the finite sum, but not always an infinite sum. Okay? But it turns out that if the power series converges at a value of x, we can actually distribute the integral and distribute the derivative across that infinite series. And that will give us a new power series, right? So if I go ahead, for example, and I distribute this derivative operator across an infinite sum, I get a new power series. And there's a theorem that says that new power series converges. And in fact, it converges to the derivative of the function. And moreover, the same thing holds true for the integral. When we want to integrate the infinite series corresponding to that function, the integral operator distributes across, and I don't know why I have a derivative there, I don't want that. The integral distributes across the infinite summation, and the result that we get is actually the integral of the function. Okay, this power series converges, and it converges to the integral of the function. And that's very important to know. That's not a trivial thing. We can't automatically assume that. But if that points in the radius of convergence, we're automatically guaranteed this. Okay, next we're going to look at how to figure out the radius of convergence for some functions.